All right, so the last example, we looked at a car going around an unbanked turn. Now we're going to look at a car going around a banked turn. Before we get into this problem, I just want to talk a little bit about what's going to happen on a banked turn. So a banked turn means that it's at some angle theta. And so we have a car here. Now, suppose that you stopped and you were on this surface. If you were stopped, then the frictional force would be holding you up. And so you would have some static friction acting this way. That's what would hold you up. So this is like the inclined plane problems that we've done before. So if the car's sitting still, static friction holds you up. Now, as you start increasing your speed, what happens is this static friction force starts decreasing and it becomes less and less until you reach what's called the optimal speed for the turn, optimal speed. So given any radius, it's a turn at which the static friction force is not there. And so this is optimal speed or design speed. Optimal or design speed. So civil engineers will design a roadway such that if you're going at the design speed, we don't care about friction. So it doesn't matter if you have ball tires or not. And then if you go too fast, if you go above the design speed, well then the static friction actually flips direction and is holding you on the roadway. So you have static friction acting this way, down the ramp. And this keeps you from sliding off the road and flying over the edge and to your demise. So this is what's happening. So this is a velocity of 0, this is a velocity at design speed, and this is velocity greater than design speed. And for this problem that we're going to do, what we're going to do is we're going to figure out what's the design speed for a given bank. So we have a curve of a racetrack. The radius is 70 meters, so we have some racetrack. We have a curve on a racetrack. The radius, 70 meters. And then it's bank at 15 degrees. So I'm going to go ahead and just draw it like an inclined plane. And this is looking from behind the car. So we have 15 degrees here. And then we have our car. At what speed can the car go without using friction? So we're going to do this type of analysis. So to do this, what we need to do is we need to get our force diagram on here. So looking at this, I have weight coming down, and weight is mg. And then I have a normal force coming up, out perpendicular to the plane, so that's my normal force. And so since it's going, let me switch back to green. Remember that it's kind of going into the page, so it's following this curve. We know that there's a net force, a centripetal force, acting towards the center of the turn. So it's in this direction. So we're gonna end up getting some components here, but you have to be careful because we're not tilting our axis. We don't care about down the bank. We care about towards the center. So we don't have to turn our x and y axis. And in fact, they're gonna stay exactly the same. They're just like this. So what we care about is what's acting in the x direction and what's acting in the y direction. And so looking at this normal, that's the one we're going to have to break down. So if I get my components on there, I see that I have a n in the x direction, and this is, again, different from the text. So you have n in the x and n in the y. And then my theta goes right up here. That's theta. All right, so there's my triangle. I'm going to go ahead and redraw this just so that you can see what's happening. So we have our normal force, and then we get n in the x, n in the y. And theta is up top. All right, so now we can start analyzing this, and we're looking for relationships. So we're going to get some relationships out of here. First, I can see that ny is going to be, you know what, actually, let's just do centripetal force. So the centripetal force in this case, the centripetal force is all due to n in the x direction. So the normal in the x direction, this piece, that's what's acting here, okay? Now we see also that ny is equal to the weight. So ny is equal to the weight. Okay. So centripetal force, remember we're looking for max speed. So the centripetal force is, we determine that by AC, mass times AC is going to be equal to nx. And my centripetal acceleration is v squared over r. So that's going to be my normal in the x direction. And my normal in the x direction, thinking about the normal force, so we have its opposite. So my normal in the x direction is going to be the normal times sine theta. All right, so we have velocity, radius and mass. We have normal. The normal, though, is not equal to mg in this case. So let's go over here and figure out what it is. So the normal in the y direction is going to be normal times cosine theta is equal to the weight, but the weight is mg. And so we see that the normal is equal to mg divided by cosine theta. Now I can take this and I'm going to plug it in this side. So we get that the mass times v squared over r is equal to the normal, but that's mg, over cosine theta times sine theta. And we want to solve for v. So first thing I'll do is the sine and cosine. Let's see, so we get m times v squared over r equals mg times sine theta over cosine theta. And that's sine over cosine is tangent, but I can also see that the masses are going to cancel. So I get v squared over r is equal to g tangent of theta. Multiplying by r, I get rg tangent theta is equal to v squared, so I take the square root, and that's my design speed. So that's without friction. This would be our design speed for a given angle. And notice it's not dependent on the wheels. So there's no static friction. It's just the radius and the angle. So the higher the angle, the more velocity, or the higher the radius. So because of that, if you look at racetracks like NASCAR, they bank them, I think Talladega's at like 24%. We also bank them on the interstate. That way you could go faster around the curves. But that's it. So just working with all the dynamics.